Okay, so this is the combination of functions homework. The one we're going to concentrate on more is the composite function. Other composites or combinations are adding or subtracting functions to create new functions, and there's really not anything spectacular about that. So here's the problem. So what we're going to do is we're going to find f of g of x and g of f of x, where we give you an f of x and a g of x. So, okay, so this is problem number 1. So you can see what f of x and g of x are. So f of g of x. Notice the notation. So we have g of x inside these parentheses. So f of x is the square root of x, and I'm going to show x. Let's use red parentheses here. So of x plus 4. So instead of plugging in x, so x is here and x is there, so what's in the argument is going to go in the parentheses instead of x. So that's the whole idea. So what we see is that g of x is x squared, so we're going to put x squared in there. And then finally what you do is you look at the simplify it. So what we could do here is we could take the parentheses away. So what we get is the answer. So for this problem, f of g of x is x squared plus 4. Now one thing you got to figure out, they don't ask, oh yeah, they do, find the domain of each function and each composite function. So, f of x is the square root of x plus 4, and for radicals, the argument of the radical has to be greater than or equal to 0. So if we subtract 4 from both sides, we'll get x has to be greater than negative 4. For g of x is x squared. Well, it's a polynomial, so you can use any real number. So we can show it as such. So the question is now, the hard part is, what is the domain of the this composite function? And the reality is that we can put any value of x in there from negative infinity to positive infinity, because you're going to square it, and so this number is always going to be greater than 0, and hence the number greater than 0 plus the number greater than 0 is also greater than 0. So what we can say is that the domain of f of g of x is also all real numbers. Okay, let's look at number 2. So f of g of x, again I'm going to use these red parentheses here. So f of x is the cube root of x. For x I'm going to put in parentheses, then plus 5. So instead of having x, we're going to substitute what g of x is into there. So we get the cube root of, instead of x plus 5, it's going to be x cubed plus 1 plus 5. And then you can simplify that down. So it's the cube root of x cubed plus 6. Now let's look at the domains for each one of these. So the domain for f of x is the cube root of x plus 5. Now for the cube root, it's all real numbers. Now why is that? It's because if I cube something, negative 1 cubed equals negative 1, therefore the cube root of negative 1 is negative 1. What number multiplied by itself 3 times equals negative 1? And the answer is -1. So because of that, x for a cube root can be all real numbers again. And then the second function, g of x, is x cubed plus 1. Well, that's a polynomial, so that's also good for all real numbers. So basically what we can say is the composite function, which is this cube root of x cubed plus 6, is also all real numbers. Now your calculators actually can help you out here if you want to try it. Just try some numbers and see. If it doesn't allow it, then it means it's not going to work. And one thing, if you want to do other than square roots on your calculator, you probably have to do fractional exponents. So we can write the cube root as the cube to the 1/3 power. So let's just try this, and we're going to do it at x equals -5. Why did I choose that? Because -5 cubed is a negative number. So if you take -5 cubed plus 6 and then raise that to the 1/3 power. So -5 cubed is -5 times -5, which is positive 25. Positive 25 times -5 is -125. So that's -119. So can we take the cube root of -119? So let me plug it into my calculator. -119 raised to the 1/3 power, and the answer is, no, didn't like that. I wonder why. So I'm going to just pause it for a second. Okay. Oh, I know what it was. I used the minus sign. Let's try that. -119 raised to the 1/3 power. Yeah, it gives you -4.92. So it is all real numbers. And looking back, I realized that I forgot to answer part of the first question. So let's go back to the first question. So I did f of g of x. So let's do g of f of x. So g of x was equal to x squared, and f of x is equal to the square root of x plus 4. So what we do is we plug in, so we can do g of f of x instead of f of g of x. So this, we're going to have something squared, whatever this is. In this case, x seems trivial, but this is the thing we're going to plug in for x. So the same thing applies here. So for what's in the parentheses is we're going to stick in this thing, which is the square root of x plus 4. And if you square something squared, you're going to end up with x plus 1. Now the danger is after you've simplified it, you would say the domain for this is all real numbers, but really we have to have it in the form before we simplify it. So you can see that before you simplify it, you cannot have x less than -4, or x plus 4 has to still be greater than or equal to 0. X has to be greater than -4. So the domain for this thing, for g of f of x, the domain is going to be x has to be greater than or equal to -4, even though this simplified version is going to work. And I'm just going to check this, double check this just to make sure. And make sure I'm doing it right here. So this is 1.739. Okay. So it says the domain of f of f and g of f of x is greater than or equal to -4. So I did that right. So that's good. I do know what I'm talking about. Okay, so let's go back here. So this one we said f of g of x, the domain was all real numbers, and I used my calculator to prove I knew what I was talking about there as well. Now, g of f of x, so what we're doing here is we have x cubed plus 3, so I'm going to do the x cubed part as this thing, something cubed plus 5. Plus 1. Now that thing that we cube is going to be the cube root of x plus 5. So this is the cube root of x plus 5. So that's cubed. Okay, so now we look at this and think about the domain of this unsimplified version. Now what we said was that the domain of this thing is all real numbers, because I can take the cube root of negative numbers and I can take the cube root of positive numbers. So that one's okay. And then if we cube anything, it's not going to affect whether it works or not. We can cube negative or positive numbers. Now let's simplify this. So if you cube this cube root, you're just going to end up with x plus 5, and then you bring down the 1. So here the answer is x plus 6. So that's g of f of x, but we use this version. So we said that version, the domain of g of f of x is also all real numbers. So we could write down all real numbers, or we could say x can be between positive infinity and negative infinity. So it turns out for problem number 2 that the domain is all real numbers for everything. So yeah, it's a little tricky, but give it your best shot. So here we have f of x is x squared plus 1, g of x is the square root of x. So let's look at the domains first. So the domain of x squared plus 1, it's a polynomial, so all real numbers. The domain of the square root of x, well, x has to be greater than or equal to 0, the argument of a square root. So that's the domain. X is greater than or equal to 0. Okay, now let's do figure out what f of g of x is. So f is x squared plus 1, but for x we put in the square root of x. So this is where we look at the domain. So because we're going to evaluate the square root first before we square it, what that means is that the same thing that applied here applies here. So I'm going to write the domain before we simplify it. So the domain is going to be that x has to be greater than or equal to 1. We could simplify it down to x plus 1. You know, if I graphed this versus that, they would look exactly the same for x greater than or equal to 0. Okay, then we have g of f of x. So f of x is that, g of x is that, so we get the square root of something, whatever the argument is in here. So the argument is going to be that. So we have x squared plus 1. Now, notice that I'm going to evaluate this first. And if I do negative numbers, I'll square it and become positive. So this thing's always positive no matter what number I use. And a positive number plus 1 is still going to be a positive number. So for the second part, the domain is equal to all real numbers. Now the only way I'd simplify this is just take away the parentheses, so I could write the composite function g of f of x as that. So this one doesn't look that much different than the original one. This one does look different when I do simplify it. Okay, and then this last one on this, oh, we got two more. Okay, so again, this is number 4, f of x. I'm going to write it down. F of x equals x to the 2/3 power. Well, what that is x squared, take the cube root of that. And so we're going to evaluate this first. And then we're going to take the cube root of that. So you can see that I can have both positive and negative values for x. Because once I plug that in, the squared is going to become positive, and the cube root of a positive number is a positive number. So everything works out great there. So this is my domain for f of x. G of x, that should be g of x, is x to the 6th. So this is a polynomial. So in the case here, the domain is, again, all real numbers. So when I make the composite function f of g of x, f of x is the cube root of something squared. That something squared is, in this case, x to the 6th. So I'm going to plug that in there. And so let's look at the domain of that before we simplify it. So the domain is going to be, well, let's think about putting positive and negative numbers in there. Well, positive numbers to an even power are still going to be positive, and then to another even power are going to be positive, and the cube root of a positive number is positive. So that works out. A negative number to the 6th power is going to be positive. Any number raised to an even power is going to be positive. So it seems like we can pretty much use any real number. Now if I simplify it, I've got, the cube root of x to the 12th power. If you have something raised to a power, you multiply the exponents together. That's the same as x to the 12/3, which is x to the 4th. So the simplified version of the composite function is x to the 4th, which also is all real numbers. So you come to the same conclusion either way. G of f of x. So what we do is we'd have something raised to the 6th power, which is the cube root of x squared. So again, we're going to look at the domain in the unsimplified version. Well, again, you can see because this innermost term is squared, that means I can, and anything squared is going to be positive, and I can take the cube root of a positive number. The domain of the composite function is all real numbers. And then I can simplify this. The way you would do that is you rewrite this as x to the 2/3 raised to the 6th power. So that's x to the 2/3 times 6, which is x to the 4th. So you get the same function. Here f of g of x equals x to the 4th, and g of f of x equals x to the 4th. They also have the same domain. And then the final one here is absolute value. So this is number 5. F of x equals the absolute value of x. If you remember, the absolute value function looks like this. So you can see it can go either positive or negative infinity. So the domain is going to be all real numbers. G of x is x plus 6, which is a polynomial. It's our simplest, well, not exactly. I guess y equals a constant. It's our simplest polynomial. So that's all real numbers. Then we look at f of g of x. So you get the absolute value of something. That's something being that. So are there any values of x where I can't evaluate this function? The answer is no. Because if I have a negative x, big enough at negative x, this will cause this to go to negative, but you can take the absolute value of a negative number. So the domain of f of g of x is all real numbers, and really can't simplify it any further than that anyway. And then the next, g of f of x is, so g of x is something plus 6. The something is the absolute value of x. So I get the absolute value of x plus 6, which are not the same as the absolute value of x plus 6. So again, we really can't simplify it any further. But are there any values of x where I can't evaluate this function? The answer is no. So that means it must be valid for all real numbers. So I'm just going to pause for just a second. Okay, continuing on. So you can see we're doing quite a number of these. It's because, you know, you got to understand the process. You got to do it sometimes. Okay, so f of x. What is the domain? Well, again, you can have positive or negative arguments in here, and so x can be all real numbers because you can always evaluate this function. Likewise for g of x, that's just a polynomial, so that's domain is all real numbers. Okay, so it looks like g of f of x should be pretty straightforward in f of g of x. So g of f of x, it's going to be f of x is the absolute value of something plus minus 4. And that something is g of x, so we get the absolute value of 3 minus x minus 4. So 3 minus 4 is negative 1, so we get the absolute value of negative 1 minus x. So that's the composite function. And the domain, we look at this unsimplified version, but again, x can take on any value because there's really there are no values that you can't evaluate the absolute value. And the same kind of thing is going to pan out here for g of f of x. So g of x was 3 minus x. But when the argument is not x but is f of x, you're going to have 3 minus the absolute value of x minus 4. And all you can do is simplify that. Well, let's look at the domain force first before we simplify it. So again, x can take on any value because I can evaluate the absolute value at any value of x. So the domain is that, and then the simplified version is going to be 3 minus the absolute value of x minus 4. Okay, the next one is a little trickier. So you've got f of x equals 1 over x. So the domain, does this function value exist at all values of x? The answer is no. You could say all real numbers except x does not equal 0. Because if x equals 0, then it's going to be undefined. So that is for g of f of x. G of x is just a polynomial. So that domain is all real numbers without any restrictions. Okay, then we do f of g of x. So f of 1 over something. In this case, the domain is x plus 3. So we haven't simplified anything, but that's really as far as you can go anyway. So what we find out here is, for this case, the domain is all real numbers except where the denominator goes to 0. So x cannot equal -3. That'll cause -3 plus 3. It gives you 0. So it's all real numbers except x equals -3. G of f of x. So g of x is x plus 3. But for x, we put in 1 over x. So you get 1 over x plus 3. So here, again, the domain is going to be all real numbers except where this denominator goes to 0. This 3 here doesn't affect the domain. So we're going to say x does not equal 0. For that, g of f of x. So I guess that's it, right? So only one of them is all real numbers. All the other ones have some restrictions on it. And then 8. So we've got f of x equals 3 over x squared minus 1. So the domain is all real numbers except when that equals 0. So you get x squared equals 1. Take the square root, you get x equals plus or minus 1. So the domain for this first function is going to be all real numbers except x does not equal -1 or +1. Or you could say x does not equal -1 and x does not equal, or x does not equal +1. So that's the domain for f of x. G of x, simple polynomial, it's just a linear equation. So the domain for this one is all real numbers. Now, f of g of x. So f of x is 3 over something squared minus 1. And that something is x plus 1. So what we have to see is x plus 1 squared minus 1, so that equal to 0, because that's where the function, the denominator cannot equal 0. So let's see what happens. So you have, multiply this out, you get x squared. So that's x plus 1 times x plus 1, which is, using FOIL, is x squared plus 2x plus 1. X squared plus 1x plus another x gives you 2x. 1 times 1 is 1. Okay, so we get x squared plus 2x plus 1 minus 1 equals 0. These cancel out. And then you factor out an x. So you get x times x plus 2 equals 0. So in this case, x cannot equal 0 because what that would do is you'd have 0 plus 1, which would be plus 1. Plus 1 squared would be 1. 1 minus 1 is 0. Okay, the other one would be x equals -2. To get that to go to 0. So you'd have -2 plus 1, which would be negative 1. Negative 1 squared is positive 1. Positive 1 minus 1 is 0. So those are correct. So what you would do here, you would say the domain for this composite function is going to be all real numbers except x does not equal 0 or x does not equal negative 2. So that's f of g of x. Then you have g of f of x. So g of x is x plus 1, but x, instead of x, we use f of x. So we get 3 over x squared minus 1. So the domain of this expression is going to be the same as the domain of this expression, because what causes this function to not exist is for this part to go to 0. So we can't have x minus 1 equal to 0. X squared equals 1, x equals plus minus the square root of 1, which is going to be minus 1 or plus 1. So the domain of g of f of x is going to be all real numbers except x does not equal negative 1 or x does not equal 1. And you see what happens if x equals 1, I'll get 1 squared, which is 1. 1 minus 1 is 0. 3 divided by 0 is undefined. And likewise, if you square negative 1, you get positive 1. Positive 1 minus negative 1 is 0. 3 divided by 0 is undefined. Okay. And I think the final problem is this one. Oh, there's 2 more problems. Okay. So these are just composite functions in word problems. So it says the pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius in feet of the outer ripple is r of t is 0.6 t, where t is the time in seconds after the pebble strikes the water. So you can see after 1 second, you're going to get 0.6, which is 0.6 meters, 0.6 feet. The area of a circle is given by the function a of r equals pi r squared. Find and interpret a of r of t, or a of r of t. It's the same, not the same thing. So this is a composite function. So a of t, well, a of r is pi something r squared. But r as a function of time is going to be 0.6 t, and then you square that. So if you think about the domain, here you can have any radius, but really you can't have a negative radius. So let's add a page. So the domain, some are mathematically possible but not physically possible. So what we would say is that r has to be greater than or equal to 0. I guess you could say it this way. R is greater than or equal to 0. Or 0 is less than or equal to r. Same thing. So that's the domain for r. And the domain for t is t has to be greater than or equal to 0. You always have to have time greater than 0. Can't make this thing go backwards. Now, if t is, so looking at the composite function, if t is greater than 0, then this argument is also going to be greater than 0. So the domain for the composite function, which would be a of t, is going to be equal to, well, if we simplify this, you'll have 0.36, that's 0.6 squared, pi t squared. So in this case, t has to be greater than or equal to 0, which will make r greater than or equal to 0. So everything's hunky-dory. So the domain of the composite function t has to be greater than 0. Composite function is just a function of t, whereas the original function was a function of r, but then r is a function of t. And the final one, you're a sales representative for an automobile manufacturer. You paid an annual salary plus a bonus of 3% of your sales over $500,000. Consider the two functions. So x minus 500,000 is your sales over $500,000. Your g of x is 3% of your salary over $500,000. So if x is greater than $500,000, which of the following represents your bonus? So you basically get up to $500,000, you just get your annual salary. But if you sell more than $500,000, you get 3% of the amount over $500,000. That's what's called your bonus. So it says which of the following represents your bonus? Is it f of g of x or g of f of x? So let's do f of g of x. So that's something minus $500,000. So that something is going to be 0.03 x minus 500,000. So that's f of g of x. And let's do g of f of x. So there, g of x is 0.03 times something. That something is going to be x minus 500,000. So, you can kind of think about this as which one makes sense to you. Think about it. Well, if I had $600,000, the difference between 600,000 and 500,000 would be 100,000. That would be my excess over $500,000, and I get 3% of that. So this seems to be the one that makes more sense. Here, you're taking your sales. So if you took $500,000, $600,000, you'd have $600,000 times 3%, which would be like $18,000. 18,000 minus 500,000 would be a negative number. So that wouldn't make any sense at all. So that's kind of my reasoning. So that's the second one, f of g of x. So if I was looking at salary, and let's say my base salary, they don't say what it is, but let's say base is $30,000. So your salary would be $30,000 for your salary between 0 and between sales between that and 500,000. So if you have less than $500,000 worth of sales, you just get your base salary. But if your sales is greater than 500,000, then your salary is going to be your base salary plus 0.03 times x minus $500,000. So you get your base salary plus 3% of your amount over $500,000. So that would be your salary. So you've got a domain for less than $500,000 sales and a domain for greater than $500,000 sales. Okay, so let's continue on with the composite function homework. So the next group of problems is to break this function h of x up into two functions, f of x and g of x. So problem number 11 is we let f of x equal the square root of x, because we have the square root of this thing, and the second part of the function is the inside. So this is problem number 11. Number 12, we have 1 over something. That's something being the absolute value of x plus 3. Yeah, you could actually make this into 3 functions, a 3-part composite function, but we're not going to get that complicated. So f of x would be 1 over x, and g of x would be equal to the absolute value of x plus 3. So when you plug this into there, f of g of x, you get 1 over the absolute value of x plus 3. Next one is 1 over the square root of x, so it's very similar. F of x equals 1 over x. G of x equals the square root of x. So f of g of x is 1 over, not x, but 1 over the square root of x. And then the final one, we have this whole thing cubed, so we'll call f of x equal to x cubed, and g of x is the thing inside, which is going to be x squared plus 2x. Okay, so that's how you break up composite functions. The last one is kind of a repeat of something we did earlier, which is doing the composite functions and then looking at the domain of the individual functions and the 2 composite functions. Okay, so the first problem, 15. So let's do f of g of x. So we plug that into there. So we get 2 times the square root of x plus 1. So that's f of g of x. Then we have g of f of x. So there we plug that into here. So instead of the square root of x, we get the square root of 2x plus 1. Okay, now let's look at the domain. This is all real numbers because it's a polynomial. This one, x has to be greater than or equal to 0. So when we get over here, again, we haven't simplified anything. In this case, we really can't simplify anything. Here, the same thing applies as did the second part here. So x has to be greater than or equal to 0, because if I have x less than 0, I have the square root of a negative number, which can't work. Here, I have to have 2x plus 1 has to be greater than or equal to 0, the argument of the square root. So if you subtract 1 from both sides, divide by 2, you'll get that x has to be greater than or equal to negative 1/2. When it's equal to negative 1/2, you'll get 0, and if it's greater than 1/2, you'll get a positive number. Okay. Next one, 16. So we have f of g of x. So that's plugging that into there. So we get the square root of x squared, x plus 1 squared plus 1. Now, I didn't do the domain of these originally. Well, we'll come back to that. Okay, again, you could simplify this by multiplying it out. But let's not do that until we figure out the domain. Then we have g of f of x. So you plug that into here. So instead of having x plus 1, we have the square root of x squared plus 1 plus 1. So the domain here is that the argument has to be greater than 0, but you can see that anytime I square x, I'm going to get a positive number. So I'll have a positive number plus 1. So this one is going to be all real numbers. the negative numbers in the domain will become positive when you square them. And this one also has the same thing because it's a polynomial, so it's all real numbers. Likewise here, any number plus 1 squared is going to be positive. So this is going to give you a positive number plus another positive number, 1. It'll make it all real numbers. And the same thing's true here, all real numbers. Because again, no matter what value of x I put in there, if it's squared, it will become positive. So that one's pretty simple. Okay, the third one, we have f of g of x. So we're going to plug that into here. So we'll have the absolute value of x, quantity squared, minus 9. And g of f of x will have the absolute value of the square root of x squared minus 9, like that. Now the domain for the absolute value function is all real numbers because, you know, if it's positive, it stays positive. If it's negative, it becomes positive. But there's no positive or negative number that you can't take the absolute value of. Now this one's a little more complicated because what we have is, you can see when x is greater than 3 squared is greater than 9, we'll have a positive argument. But if x is less than 3 or greater than negative 3, you'll end up with a number less. If you take a number less than 3 squared, it's going to be less than 9, and this one will be negative. So it turns out the domain for this one is going to be from negative infinity to negative 3, including negative 3, because that'll give you 0. And then it's from positive 3 to positive infinity. So it's all real numbers except the numbers between negative 3, positive 3, not including 3. Okay, so now what will happen over here, the same thing will apply, the same domain here applies for the second composite function because, you know, the absolute value of any number is going to be okay as far as the domain. The only thing that's going to mess this thing up is going to be whether the argument of the square root function is negative. And that's what messed it up here as far as not making it something that you can evaluate. So this one's going to have the same domain. Now here, if you take the absolute value of x, it's going to become positive. So it really doesn't affect anything, because if you square something, it becomes positive. If you take the absolute value of something, it's going to become positive. So it's kind of redundant. This absolute value, once you square it, doesn't really do anything. And so it's going to have the same limitation as far as x is concerned. Because whether you have -1 absolute value and you square it, or you have -1 and you square it, you're going to have the same result. So both of these have the same domain, which is limited by the fact that the argument of the square root has to be positive. And then the last one, number 18. Let's just look at the domain here first. This is going to be all real numbers because it's a polynomial. And here it's everything except x cannot equal 0. So it's all real numbers except x cannot equal 0. Okay, so the composite function f of g of x, there we plug in 1 over x into here. So you get 1 over x squared plus 3 times 1 over x minus 4. And again, the unsimplified version is going to set the domain, and so it's going to be all real numbers except x cannot equal 0. Because when x equals 0, both of these are going to become undefined. For g of f of x, what happens there is we plug this into there. So we get 1 over x squared plus 3x minus 4. And so the values of x that we're looking at are the ones that make it so that the denominator cannot equal 0. So what we'll do is we'll solve this for when they do equal 0. And then we'll say, okay, actually we don't want them to equal 0, so that'll be the domain. Here we're solving this equation for the zeros. And I set this up so that you can factor it by observing it. So what two numbers multiply together give you 4, 1 and 4, 2 and 2. Which one has a difference where the difference is 3? So you have 4 and negative 1. So you can see if I multiply this out, I get that. So the denominator is going to go to 0 under two conditions. When x equals negative 4 or x equals 1. It's equal to negative 4, this parenthetical expression goes to 0. When it equals 1, this one goes to 0, and 0 times any number is 0. So our domain here for this second problem, or the last problem, is going to be all real numbers except x cannot equal negative 4 and x cannot equal 1. There's another way to write this. You could say from negative infinity to negative 4, negative 4 to positive 1, positive 1 to positive infinity, but not including either negative infinity or positive infinity or negative 4 and positive 1.